Today, we're going to share with you the easiest way to explain Gauss's law. We know that this topic has a lot of formula for you to remember. May this video helps you to understand more about this chapter.
Hi everyone, so right now I want to do the introduction for the gaseous state. So the first one is the properties of gases. Firstly, we all know that gases have more empty spaces between particles comparing to liquid and solid. After that, gases have no definite shape or volume, so gases assume the volume and the shape of their container. Lastly, gases are also highly compressible, which means it can mix well in any spaces. For example, the balloon right here.
So, the first law that we are going to learn is Boyle's law. What is the thing that involved in Boyle's law? Ta-da! This is the formula that includes the changes of the pressure and the volume. Now, I would like to share a short story with you as an example. Few kids was going out happily with their friends, and the kids represent the gas particle. Suddenly, they were shocked with the presence of dragons. Now the dragons represent pressure, and the space between the kids are the volume. The dragons start attacking the kids and give pressure to them. Now that the kids are scared, they get closer to each other and the volume is decreased. In Boyle's law, you need to remember that when P increases, volume will decreases or vice versa. It is concluded here that pressure is inversely proportional to volume and temperature remains the same.
This is the second gas law, which is Charles' law. So, let's move to the formula. It is V1 over T1 equals to V2 over T2, where V is the volume and T is the temperature. This is the example that I made. As you guys can see, these few kid penguins represent gas molecules that fuse together during low temperature. The space between the penguin is actually the volume, and the rainy weather represents the temperature. So, let's watch this animation together. During rain, all the penguins will stick together tightly until there's no gap between them. Suddenly, the rain stops and the sun finally comes out, and it's starting to get hot. These penguins will distance themselves from each other so they will not feeling hot. Suddenly, the sun keeps getting hotter and all the penguins run from each other. This shows that as the temperature increases, the volume also increases. So, to conclude from the example that I gave before, volume is directly proportional to temperature.
Now, we're going to learn about Gay-Lussac law. It describes the relationship between temperature and pressure. When the volume and amount of gas is constant, pressure and temperature are directly proportional to each other. The formula for Gay-Lussac law is P1 over T1 equals to P2 over T2. So here's an example. The teacher is mad at the student because he failed the test. When he has a lot of pressure around him, his temperature will increase. This can conclude that when the pressure increases, the temperature will also increase because they are directly proportional to each other.
This is Avogadro's law with the little bunny as a number of gas particles or moles. And the pink space will be the volume. The two little bunnies are shocked when fluffle of bunnies suddenly emerging them. This animation illustrated that gap and space between them increase. Suddenly, more bunnies rush to them and increase the volume. From this little bunny example, it shows that as a number of moles increase, the volume will increase too. Oopsie, I almost forgot to tell you about the formula. It is V1 over N1 equals to V2 over N2. You need to remember, okay? To conclude, volume is directly proportional to number of moles. That's all. Bye-bye.
Okay, let's move on to something that's a little bit more complicated. Ideal gas. This is the formula that you must remember. Pressure times volume equals to number of moles times gas constant times temperature. Okay, imagine a room is filled with kids running around, but now the kids represent gas particles. The frequency of kids crushing the wall is the pressure. The size of the room as volume. Speeds of kids running as temperature. And number of kids as number of mole. For example, if we increase the speeds of kids running, which is the temperature, the kids will crash the wall more frequently, causing the pressure to increase. So what we can conclude from this theory is that pressure is directly proportional to temperature, while volume and number of mole remain constant.
Density and molar mass. Now I want to show you the formula for density and molar mass. The first one is the M equals to dRT over P. And the second one is D equals to MP over RT. M stands for molar mass, D for the density, R is the gas constant. The gas constant is 0.08206. T is the temperature. Temperature should be in Kelvin. P is the pressure. Same goes to the second formula as well. The density of a gas is directly proportional to its mass, which means if the density decreases, then the molar mass also decreases.
Now, we're going to learn about Dalton's law. As an example, we have two different gases, which is oxygen gas and nitrogen gas, with 156 mm mercury of pressure and 597 mm mercury of pressure. When we add these two together, we'll get 753 mm mercury of pressure. Here, we can conclude that oxygen gas is equals to P1 and nitrogen gas is equals to P2, and we can get the P total. When each gas exerts on its own, we call it partial pressure. In conclusion, the partial pressure of the individual gas will add up to the total pressure. Now, let's talk about mole fraction. In this topic, we use the formula PA equals to XA times with PT. PA is the partial pressure of gas A, while XA is the mole fraction of A times with the total pressure. So here, we know that mole fraction is the ratios of the moles of a substance in relation to the mole present.
Yeah, already know guys. Here helps look. First, a fusion. It is a process by which a gas escapes from its original space into an evacuated space through a tiny hole. As you can see, the gas in the balloon escaped through the mouth of the balloon, which is the tiny hole. Next, diffusion. It is a process of gas movement of one gas through another. This process occurs through the particle to achieve equilibrium, as shown above. Here's the formula to calculate the rate of fusion.
Deviation from ideal gas behavior. As we know, ideal gas has no volume, and also space between gas particles is bigger than the size of particles. So the first one is the kinetic molecular theory. Kinetic molecular theory is applied to gas and it has 5 basic assumptions. The first one is that particles have negligible volume. Secondly, particles have no intermolecular forces. Behavior described by PV equals to nRT. The third one is gas are in continuous random motion. This means that the gas never stops. Fourth, the gaseous particles are perfectly elastic. For example, it bounces back. Lastly, the average kinetic energy of gas are in absolute temperature. Deviation from ideal gas behavior happens at 2 conditions. First is at high temperature, second is at low temperature. So this is what happened on the low pressure. It is decreases in kinetic energy and has no impact on intermolecular forces, which means there are none. And this is what happened on the high pressure. The particles' volume are still negligible compared to the size of container. Ideal gas versus real gas. Firstly, ideal gases is volumeless. However, real gases is finite volume. After that, particles do take up space. And also, volume of the gas is actually bigger than the volume of the container. Secondly, ideal gases do not interact with each other. Real gases particles do not interact with each other as well. Lastly, ideal gases molecule would travel in a straight line. However, real gases path would curve due to the addition between molecules.
as easy as A, B, C, D.
That's all from us. Thank you.